Okay, we did some calculations on titrations last week. I would like us to see some problems now from past exam papers that involve titrations and generally mole calculations and so on, to see how they appear, because usually they are part from other problems. So here I have the first problem. This one does concern titrations. Let us read it carefully. In a titration, a student added 25 cubic centimeters volume, that is, of 0,200 moles per cubic decimeter aqueous sodium hydroxide to a conical flask. So this is our standard solution of known concentration. Okay. The student then added a few drops of methyl orange to the solution in the conical flask. Dilute sulfuric acid was then added from a burette to the conical flask. The volume of dilute sulfuric acid needed to neutralize the aqueous solution of hydroxide was 20 cubic centimeters. So this is the volume of the acid that we added. Okay. So they give us here the neutralization reaction. What was the color of the methyl orange in the aqueous sodium hydroxide? They mean before we added the acid, when it was just the base with an indicator, and obviously when we add the methyl orange in the basic solution, the alkaline solution, it's yellow. I hope you remember we saw the video, we watched the video last time where this lady added the methyl orange in the flask where there was sodium hydroxide. So it was yellow, and then after it was neutralized, it became like orangey. The next question says, determine the concentration of the dilute sulfuric acid in grams per cubic decimeter. So you see, they ask us to find the concentration, not in moles per cubic centimeter, as is the most common request in this problem, but in grams per cubic decimeter. And actually, that is the reason why I chose this problem, because we need to have one example where we find the concentration in grams per cubic decimeter. But now I want you to take a look at this question. Okay, maybe I should reduce the page a bit so that you can see the whole of it. You see, they tell us to find the concentration of the dilute sulfuric acid, but these dots here, actually, they show us the step of how to go about. So if we follow all those steps at the end, we end up finding the concentration in grams per cubic decimeter as they ask. So be careful when you see those dots. They actually split it into the steps that we have to follow. So now that you can see we have 1, 2, 3 dots, four dots to go. Let us make it a bit larger so that we can write here. Now, the first step now, calculate the number of moles of aqueous sodium hydroxide added to the conical flask. You see, we know that in the conical flask, we have put 25 cubic centimeters of this known concentration of 0,2 moles per cubic decimeter. And we are asked to find the number of moles, in other words, the N, to find the amount, in other words, of sodium hydroxide in the conical flask. And in general, what is the formula that gives us the concentration of a solution? The concentration of this sodium hydroxide in the solution is number of moles, the amount, in other words, divided by the volume of the solution. And here we just need to solve for N, because this is what they ask in this part. So the number of moles is concentration times volume. And what is the concentration of sodium hydroxide? It's given 0,200, they say, moles per cubic decimeter times the volume. The volume is 25 cubic centimeters. Remember, we need to change it into cubic decimeters. So we need to divide by 1,000 to change it to cubic decimeters. Okay, so now this is what we need now. We would just have to do the calculations now. And what do we find here? We find this is 0,005 moles. So our answer here is 0,005 moles. So in the flask, in the conical flask, actually we have 0,005 moles of sodium hydroxide. All right. The next now, calculate the number of moles of dilute sulfuric acid added from the burette. Okay. Now we need to go to the equation here because this equation corresponds to the neutralization of the acid and the base together, the neutralization reaction, and we see that it's 2 to 1. The moles of the alkaline sodium hydroxide to the sulfuric acid is 2 to 1. So if we have, we found the number of moles of sodium hydroxide, obviously the moles that reacted with of the sulfuric acid is half of the sodium hydroxide. So here are the moles of sodium hydroxide. Obviously the sulfuric acid is half of these moles because it's 2 to 1. So so it's 0,005 moles divided by 2. That will be the number of moles of sulfuric acid, and this is 0,0025 moles of sulfuric acid. So these are the moles of sulfuric acid. We also know its volume because we measured it with a burette. Now, calculate the concentration of the dilute sulfuric acid in moles per cubic decimeter. In other words, the normal concentration. What is the concentration of sulfuric acid? In general, the formula is amount divided by volume. Here is the amount. We found it just now. So this will be 0,0025 moles divided by the volume, which is 20 cubic centimeters. But you remember, we need to, I'm just saying 20, not 20,0, but we need to divide this by 1,000 to change it into cubic decimeters. So I will write it like that in this notation. To convert, in other words, the 20 cubic centimeters to 20 to cubic decimeters, okay? And here now, if we do our calculations, we find the concentration of the dilute sulfuric acid. Calculate the concentration. What is this? 0,125 moles per cubic decimeter. Okay. So there is our answer here, 0,125 moles per cubic decimeter. All right, so this is the concentration in moles per cubic decimeter. And now the last step, finally, we are going to find the concentration of the same sulfuric acid in grams per cubic decimeter rather than in moles. Okay. Well, we know that, first of all, how do does the amount of a substance relate to the mass of the substance? The number of moles, in other words, is actually the mass of the substance divided by the molar mass, isn't it? So this is what we need to find here. We have the number of moles here. We have it. We also need, though, to calculate, to determine the molar mass of sulfuric acid. Actually, the formula mass. So for this, now we will be needing some values from the periodic table. Where is the sulfuric acid? Where sulfuric acid has, this is the formula of the sulfuric acid. We have 2 hydrogens, so it's 2 times 1 plus 2, plus sulfur, 1 sulfur. Sulfur from the periodic table is 32. Yeah, its relative atomic mass is 32 for sulfur, plus 4 times its oxygen has relative atomic mass of 16. Okay, and this one will give us it all together is 98. This is the relative formula mass of sulfuric acid. 98. So there we have this value that we need here. So from there now, if we solve for the mass, if we solve this equation for mass, this will be amount times the relative formula mass of sulfuric acid. So this is 0,125 moles per cubic decimeter times the 98. And this should give us what? 12,25 gives. So here is our answer in grams per cubic decimeter, 12,25 grams per cubic decimeter. So there is some alternative concentration of a substance that is given in these units of grams per cubic decimeter. All right, because, and it's good to know how to do that, because very often they ask for the concentration in terms of grams per cubic decimeter rather than moles per cubic decimeter. All right. If there are any questions up to this point, you can send a message in. Okay. Now let's see what is in the next page here in this exam I'm looking. Yeah, let's continue in the next page. It's not about concentrations, but it's something that we should be able to do it. Let's look here. The same question continues. It says iron sulfate decomposes when heated strongly, and here they give us the composition of the iron sulfate. And they say 15,20 grams of iron sulfate, 15,20 grams of iron sulfate was heated and formed 4,8 grams of iron oxide, of the oxide of iron, this one. And they give us the formula masses of these two oxides, of the oxide and of this salt, so that we don't have to calculate it. And they ask to calculate the percentage yield of this reaction. All right. I hope you remember the percentage yield. Now let us see. So it's again about calculations, quantitative chemistry. So we have the equations, and we know that we are told that 15,20 grams of this iron sulfate, so 15,20 grams of this thing, was heated, and the result, one of the products, the iron, the oxide of iron, was 4,80 grams. So that was 4,80 grams formed. All right. So this is what was formed. Calculate the percentage yield. If we remember, the percentage yield is actually yield is actually the product, the quantity that was formed, the actual, in other words, the actual mass, or the actual quantity that was formed, divide by the expected quantity, the actual divided by the expected times 100 to change it into percentage. So we are given the actual quantity, the actual mass of the iron oxide. But in theory now, let us see, if 15,2 grams of iron sulfate decomposes, what is the expected quantity of iron sulfide that should be formed? So let us find that doing some calculations here. So we see that, okay, the reaction is here and it's already balanced. So we see that the ratio of iron sulfate decomposing to the iron oxide formed is 2 to 1. Okay. So we need to find how many moles of iron sulfate this 15.2 gram represent? So we know that 1 mole of iron sulfate has a mass of 152 grams, because this is the relative formula mass of iron sulfate. In our case, where we have 15.2 grams only, how many moles is that? And if we solve for x, we find the number of moles of iron sulfate that we had in this situation, and we can see here, it's 0.1 moles. Do here the calculation, 0.1 moles of iron sulfate. All right. So since the ratio of iron sulfate to the iron oxide formed is 2:1, in other words, now that we have 0.1 moles of iron sulfate, it's only half of these moles of iron oxide that was formed. So the moles of iron oxide formed is actually half of that, which is 0.05 moles. In our case, this is what, in theory, the number of moles of iron sulfide formed. And now that we have the number of moles, the expected moles, we can find how much mass does this represent. So we know that 1 mole of iron oxide of this type has a mass of 160 grams. In our case, where we have 0.05 moles, how many grams does this represent? And if we do the calculations here, we should find that the grams, the expected mass that from here is how much. Let me see my calculations here. Do I have it? I have no idea where it is. I don't know. Let me do the calculation here in the calculator. 0.05 times. Oh, I did it differently here. That's why I don't have the values. Yeah, no problem. 0. Anyway, I find here 8 grams, and I don't know if my calculations are correct. All right, so these 8 grams, how many moles does this represent? Yes, I did it the long way. All right, so, okay. Now that I have 8 grams of iron oxide, how many moles is that of iron oxide? So this is now the actual, the moles that I am expected to have here. Sorry, let me do my calculations here. Yeah, 0.05. Oh dear, stupid. I had this number, sorry. I'm losing my mind here. We know that this is 0.05 because we knew that already. Do I have to calculate? Yeah, sorry about that, yeah. Okay. Now, where am I now? So these are the moles we said of, hold it, let me find my, this is of iron sulfate. And these are the moles of iron oxide, the expected moles produced. But now, okay, the expected moles produced, which are 8 grams, fine, sorry. Yeah, 8 grams, but the actual production of iron oxide is only 4.8 grams. As you can see, it's less than what was expected. I was expecting 8 grams in theory, but I only got 4.8 grams, which obviously let us use these values and see if we can find the yield, the percentage yield. Let's see here. If we have the actual mass that we got is 4.8 grams, and the expected mass in theory, that should be 8 grams times 100. Does it give me now the correct value? Let's see how much does this give us. 4.8 divided by 8. It's 60%. Yeah, that is correct. So this gives us 60%. So the yield, the percentage yield that we are asked to find is 60%, because this is what we got, and this is what we would expect to get in theory if everything, we had no any losses and everything was perfect. So it's only 60%. Okay, we could find it in a different way as well. Instead of finding the mass, the expected mass, I could use calculations with moles, but it doesn't matter. Both ways are correct. So, are there any questions in this problem and the previous one with a titration? If not, we can leave this problem and do something else. I mean, move on with another question. Okay, let's open another question. Let's see what can we do here. Let's do this one. As you can see, this type of questions are mixed with questions from other sections, not necessarily with calculations or titrations or concentrations. And in this question number 3, this is part of question number 3 of a recent exam paper from this year, actually. And part B now concerns the topic that we are covering now with mole calculations and so on. Let us see what it says. Okay, pen. Some airbags contain sodium azide. When a car airbag is used, when a car airbag is used, the sodium azide decomposes. So this is the formula of sodium azide. And when you listen to the word sodium azide, you don't need to panic, because something that I'm sure you have never heard before, because they kind of give us its formula and they tell us how it is used and how they give us even the equation here. So don't panic when we hear something which is unknown. Usually they give you enough information to get you started, okay? So don't get startled if you hear something unknown. So the equation of the decomposition of sodium azide is shown here. They give us the equation, you see, and they give us the formula of sodium azide. Calculate the mass in grams of sodium azide needed to produce 144 cubic decimeters of nitrogen using the following steps. Now, again, they tell us the steps to follow until we end up to the final answer, which is calculate the mass in grams. Okay, so here at the end is where we are going to find the mass in grams. So actually, it's not really hard to solve it. It's just we need to follow step by step what they tell us, and we are not going to get stuck. In other words. All right. So first, calculate the number of moles in 144 cubic decimeters of nitrogen, measured at room temperature and pressure. So the only thing that we need to know here is to remember that 1 mole of any gas has exactly the same volume, occupies the same volume at room temperature and pressure, which is what? 24 cubic decimeters, isn't it? 1 mole of any gas occupies a volume of 24 cubic decimeters. They need to see that we know that. So now that we have 144 cubic decimeters, how many moles are these? And we do the calculations and we find this number of moles. This would be what, 6. The answer is 6. So in other words, 144 divided by 24, do the calculations here, that will give us 6. So the answer is 6 moles of nitrogen. Okay, there is the nitrogen. No, here's the nitrogen. 6 moles of that are produced. Determine the number of moles of sodium azide needed to produce this number of moles. Okay, so now that we know the number of moles of nitrogen, we need to find the number of moles of sodium azide. And note that the ratio is 2 to 3, so we need to be careful here with this ratio. Now that we have 6 moles of nitrogen, how many moles of sodium azide does this correspond? So how we need to consider this ratio. So the 6 moles here that we have times the ratio here 2 to 3, which is 2 over 3. That should give us the number of moles of sodium azide, isn't it? Which is, this is 4. This is 4 moles. Okay, so this is 4 moles here. 4, and this is 6. You can see the 4 to 6, it's actually the same as 2 to 3. Now, calculate the relative formula mass of sodium azide. Well, the relative formula mass is the relative atomic mass of sodium plus 3 nitrogens. So, sorry. What is sodium is 23. We need to find from the periodic table. Yes, 23, isn't it? Yeah. 23 plus 3 times the atomic mass of nitrogen, which is 14. Okay, so this is 65. So there is the formula mass, the relative formula mass is 65. Calculate the mass of sodium azide needed to produce 144 cubic decimeters. So finally, now that we have all this information, we can calculate now the mass needed to produce this volume of sodium. Well, we have the amount in moles of sodium azide. We can find its mass. So we have 4 moles of sodium azide, and if we to change it into which is 65 grams per mole, isn't it? Each mole is 65 grams, isn't it? The mass of each mole is 65 grams. So we simply multiply 4 that we have here times 65 grams per mole. And what does this give? 260. And this is our answer, which is 260 grams. So in other words, we change those moles into the mass they represent. It's 260 grams. And we find it. So you see, this is another question that they ask a mass, but they kind of guide us step by step how to go about. So they make it actually easy. And we just need to know basic things, like we need to know that 1 mole of gas at room temperature and pressure occupies the same volume, which is 24 cubic decimeters. And we need to know how to find the relative formula mass of things. So these standard things that we need to know, and how moles relate to mass, isn't it? Mass per molar. How the number of moles, the amount of a substance, is linked to the mass of a substance. These very basic things that we need to be aware, and if we know those things, we can solve this type of problems. All right. We need to stop because if you need more problems on this quantitative chemistry, you can let me know that we can do some more, or else maybe we can, from next week, maybe we can start with the organic chemistry to do some organic chemistry as well, because it's a big topic, the whole. So guys, I hope you'll enjoy your weekend, the rest of your week, and